Hello friends, so today we are going to discuss three questions, and these three questions are from electrostatics. And the first question First question is, ask that two rings with radius r having charge q and minus q, so this will be our plus q, uniformly distributed around them. The rings are parallel and located at a distance h apart as shown in the figure. Let z be the vertical coordinate with z is equal to 0 taken to be at the center of the lower ring. As a function of z, what is the electric field at points on the axis of the rings? In this case, we have to find out the electric field on the axis between the rings, and we have two discs, so we can just draw an approximate figure. So this is our suppose upper disc, and this is lower disc, and they are concentric with each other. And it is given that the distance between the disc is given as our h, and so radius is same. So r is the radius of the upper disc and r is the radius of the lower disc. And upper disc, let us suppose, is having a charge of minus q, and the lower disc is having a charge of plus q. And it is also given that the lower disc is at the origin, okay, when z is equal to 0. One second. Yeah, z is equal to 0 is taken as the lower disc. So it means that upper disc will be centered at z is equal to h. So this is lower disc at z is equal to 0 and upper disc is z is equal to h. So we have to find out the field point on this common axis, okay, that is between 0 and h. And we know that, okay, let us write the things which are given to us, then we can so first we have two coaxial rings, and each is having a radius of r. Then we have a lower ring, and lower ring, let us suppose, is having a charge of plus q, and it is given that it is centered at z is equal to 0. And then we are having upper ring, and upper ring, the charge is our minus of q, and it is centered at Z is equal to H. So we know the standard formula that electric field on the axis of a ring, that formula we already know, so we are going to use that formula for both the cases. Okay. So we can say that electric field on the axis of a ring at a distance Z from its center. And let us call this as our E of Z at a distance Z will be equal to 1 upon 4 pi epsilon naught, and this comes as Q times Z divided by Z square plus R square, and we have this as 3 by 2. And let us suppose Z is somewhere here. So this is our Z. So from the upper disk, the distance will be H minus Z. And so this is from our, you can say, the lower disk and lower ring rather. So we can say that field due to upper ring, and the upper ring is, let us call this as E1, and this we are going to call as E2 along the Z axis, and that will be equal to over E2 along our Z axis will be 1 upon 4 pi epsilon naught, and charge is our minus of Q, and the distance is our H minus Z. And this will be coming as our H minus Z, and we have our Z square plus R square, and this our 3 by 2, and this is our Z unit vector, and this will be also our Z unit vector. So the net electric field will be nothing but the superposition at point Z. So you can see total field that is our E of Z will be equal to our E1 plus E2, and we can simply substitute it. So we get our E of Z is equal to 1 upon 4 pi epsilon naught, and this becomes our QZ divided by Z square plus R square, and this is our 3 by 2 minus Q, and this is our Z minus H upon Z minus H whole square plus R square, and this comes as our 3 by 2. Okay. Sorry, not z minus h, but this is h minus z. And therefore you can say, one second, my mistake, because we are moving in downward direction. Okay, so this entire thing will be having a reverse sign. So this will be minus, this will be plus, okay. And same thing is going to hold here also. So this will be z minus h, and this also z minus h. And we can just sort it out. So this comes as 1 upon 4 pi epsilon naught. We can take q as common. So this comes as z upon z square r square 3 by 2 minus z minus h divided by z minus h whole square plus r square, and this is over 3 by 2. And we can just make some, you can say, we can divide this into subparts. For the sub first, if you say, if our z is very much greater than our r, therefore under this condition we can say that this will behave like a dipole. Okay. And another thing, if we say that our z is our h by 2, it means the point is exactly at a midpoint. So from here we can say that we are going to get a maximum field, or we can say strong field rather. We are going to get a strong field because both lower as well as upper disk contribute in same direction. Both contribute in same direction. Okay. So this question was quite straightforward. Okay. The only thing we have to take care of is the direction. Okay. So lower one is having a plus q. Okay, the point is above it, and the upper one is a minus q, but the point is below it. So we have to take a negative of it. Okay, so this mistake I made in the first attempt, but later on I corrected it, so it has to be reverse. This is the only thing we have to take care. Otherwise it is quite simple, not much of calculation is required. Come to the next question, and it states that this basically has a 3 subparts to it. A hole of radius r is cut out from a very large flat sheet with a uniform charge density rho sigma. Let L be the line perpendicular to the sheet passing through the center of the hole. What is the electric field at a point on L at distance z from the center of the hole? Part B, if a charge minus q with the mass m is released from rest on L very close to the center of the hole, show that it undergoes oscillatory motion and find the frequency omega of this oscillation for these given values. And part C, if a charge minus q with the mass m is released from rest on L at distance z from the sheet, what is its speed when it passes through the center of the hole? What does your answer reduce to a large L z? Okay, or we can say as compared to this z is very much larger than our r. So this is having our 3 questions. And so electric field in the first case, in the first question, we saw that we can apply a superposition principle. Okay, and same thing we are going to apply for our part A also, here also. Okay, and please take care that superposition is to be applied by according to their sign. Okay, so this is basically superposition, but we have to take care of that sign. So in part A, so we are going to use that we are having a sheet with a hole whose electric field we are supposed to find out. Then it's in general, according to the superposition, we can say that we are going to consider it as an infinite charge sheet minus charge disk of radius r, the portion which I have removed. Charge disk of radius capital R. Okay. So this will be our basic formula to find out the electric field. And so let's find out. Okay. So we can just